In Chapter 11, we learned a whole mess of different formulas and hypothesis tests, and so we really need to take a moment and make sure that we've grasped everything and kind of organized it all in our mind. So let's begin with the population confidence interval formulas for two populations that we saw in this chapter. So we saw in section 11.1 the confidence intervals for the difference in two proportions, and then 11.2 the difference for two means with dependent samples, and then 11.3 the difference between means for independent samples. So let me grab the pages on the notes packet that's at. There, and in the current semester that I'm making this video, it's on page 330. Keep in mind if you're watching this in a later year, it might change or alter. But right now it's on page 330. The double proportion one's at the top. The middle one is the matched pairs mean, and then the bottom one is the independent mean. There, I think the easiest way to write that is the top box, part 1, part 2, and part 3. Part 1 being the top of that top box, part 2 being the middle, and then part 3 being the bottom. Now, the formulas for 11.1 and 11.3 in particular are just horrendous. They're absolutely terrible. So let me go back and show you those real quick. So 11.1 in particular is just awful because it has this huge square root with all these p hats floating around. So remember, for that section we just use the calculator to find this interval. We're not going to do this formula by hand. And we're particularly not going to do 11.3's formula by hand, even though the formula is actually a little bit easier. But the problem is that your degrees of freedom, if you recall, is absolutely horrendously awful. It's a huge formula. This textbook kind of gets around that by using the smaller of n1 minus 1 or n2 minus 1. That's not actually accurate. It's not perfectly accurate. So we're just going to use the calculator to come up with those. Now the one that we can do is the middle one, the matched pairs mean one. That's pretty straightforward. It's d bar plus or minus t alpha over 2 sd over the square root of n, where the degrees of freedom was n minus 1. Now what statistics are we using, and what kind of parameter are we estimating with these particular values? For the proportion ones, you're using the sample difference between the two proportions. So the difference in one sample's proportion versus the other sample's proportion. So p1 hat minus p2 hat. That's your point estimate, that difference. You're using that to estimate where you think the difference in the population proportions is. And to simplify that out, so the difference in sample proportions, that difference is your point estimate, and that's estimating where the difference in the population proportions is. And that difference is what you're trying to get a handle on, because you don't really know what it is, you just know where you think it is. Okay, now the same thing is true for the difference in matched pairs. The thing is that with the difference in matched pairs, we use the d bar, which is your differences of your the mean of your differences, if you'll excuse me, to estimate where you think the mu for the differences is. There. Now remember that the second one in particular works a lot like chapter 10, because because they're matched pairs, you're able to find the difference values, and the difference values are actually what you're doing the hypothesis test on. So you find a row or a column of all the differences, and from that you find your standard deviation, SD, you find your d bar, which is your sample mean of those differences, and you use those to gauge where you think the population mean of all differences of this type would be. Now 11.3 with the independent means works a lot more like proportions. They're two separate groups. They're not matched. So you have x bar 1 and x bar 2, and the difference between those two is your statistic. And then the mu 1 and mu 2, the difference between those two is your parameter. And because these don't have that matched pair quality, you're not able to find the differences and then perform calculations and hypothesis tests, or confidence intervals for that matter, along those means, along those differences, like we were for 11.2. So 11.2 is really this kind of special case of that matched pairs design. But for 11.1 and 11.3, you basically have two separate groups, and you're basically hypothesizing where you think the difference for them is going to fall, at least for when you're making confidence intervals. Now, how you spot which interval you're doing is a lot trickier, so you'll have to pay close attention to what the words are saying in the problem. Well, first of all, how do you know it's a confidence interval problem in the first place? And you'll look for words like construct a confidence interval. I mean, it's pretty straightforward, but not how big a sample do I need to construct a confidence interval? That's a different problem. But just straight up construct a confidence interval, blah, blah, blah. Now, the proportion ones are a little bit easier to tell because you'll see proportions somewhere, and they'll talk about two separate portions or two separate groups, and they'll either give you proportions or they'll give you the stuff to make proportions, like x and n. So if they give you x's and n's and then talk about proportions, then that's a proportion problem. Now, the mean ones are a little bit trickier because they can look very similar. But the thing about the 11.2 type of mean is that it's going to have a matched pairs data set somewhere, or it'll talk about a matched pairs problem. So if it's talking about a dependent sample where one group and the other group are interconnected, then that's matched pairs, and that means that you're doing an 11.2 type of confidence interval. Also, you're going to be asked about the means or the averages. They might not give those values to you because, quite frankly, they usually, or not usually, but often want you to come up with the D bars, or excuse me, the D values yourself, the difference values yourself, then find D bar and SD and so on. But it's possible they would be given to you in the problem. But you want to look for things like husbands and wives, brothers and sisters, twins, those kinds of things, or before and after. Before and after is a big one. That's all matched pairs, and that would be 11.2. Now 11.3 is going to talk about means, but they're different data sets that are not related in the same way a matched pairs data set is. So maybe one column is longer than another. That's kind of a red flag that you're dealing with independent samples. And they'll talk about the means, or they'll talk about the data set, and it's an independent data set, but it's not talking about proportions, because proportions would be an 11.1 problem. So these are going to be trickier for you to figure out, but you're going to have to read very carefully into the problem. Figure out if we're talking about two groups, because if we are, we're in chapter 11. Are we being asked to construct a confidence interval? And then what kind of information were we given about this? Is it proportions? Is it means? Is it matched pairs, not matched pairs? Keep in mind, you also have to keep these straight from the chapter 9 values, which chapter 9 was constructing a confidence interval for single proportions and single means, which I have right here. So single proportions and single means, you still had the construction of a confidence interval, but it's only talking about one population, one group. Whereas chapter 11 is talking about two groups and how they differ from each other. Men, women, husbands and wives, before and after, that kind of stuff. That's chapter 11. Now, as for the requirements we have to check, they're kind of the same requirements we've been having, well, since chapter 8, quite frankly, which is when they first came into play, because these requirements are built out of the central limit theorem. Namely, we need things to be normal, random, we need independence, and we need normality. So there's a lot of requirements, but there's just more of them. And there is one added requirement. So we need the samples to be random. For proportions, we would need the samples to be independent of each other. Then we need those same samples to be independent of the population. This is what we were checking back in chapter 8 and 9 and 10, which is that our sample size is less than or equal to 0.05 of our population size, right, for both samples. And then we would also need to check normality, and our rule of thumb for that is n times p times 1 minus p is greater than or equal to 10. So we have to check all of those things first, and then you could construct the confidence interval. For the difference between for the mean for dependent samples, you would need to check that the sample is random, but that it's dependent, of course, because we're trying to find those differences in the before and after, or that matched pairs design. Then you need to check that the sample is independent of the population, and that the sample comes from a normally distributed population, and we check that with either it being given to us somewhere or a normal probability plot graph, or we use the rule of thumb that n is greater than or equal to 30. Remember, we can use 30 for means, but we cannot use that for proportions. And furthermore, remember that this whole checking that the sample is independent part, you only have to worry about that if your sample is taken without replacement. If it's with replacement, then you're fine. You don't have to worry about it. It's already independent. But if it's without replacement, then we kind of have to fake it by taking a small enough sample that it doesn't affect the larger population. Now for the difference in two independent means, you would need the sample to be random and independent as opposed to dependent, and you would need to check everything again. So you need each of those samples, because they're independent, you have to check that each one of them is independent of its population. Then you need to check that each of them is normal. So you have a little bit more work to do with an 11.3 problem and an 11.1 problem than with 11.2, because 11.2 is everything breaks down into those differences, and that's all we kind of consider. Now the calculator entry for these is pretty straightforward. For the interval for two proportions, it's the 2 prop z int. And if you look at the table, I actually tell you that it's that right there in that gray highlighting, 2 prop z int. And down here you can see the gray highlight t interval and 2 samp t int. So that's what they are, t interval and 2 samp t int. Now it's interesting to note that the t interval is actually the same interval we were using back in chapter 9 for a hypothesis test for for a confidence interval for a single mean. That's because when you're looking at a dependent sample, all you're considering is the differences, and the differences work like they did in chapters 9 and 10. So it's the same interval formula we used in chapter 9. And then the probability distribution you're using is rather obvious, because it tells you right in the calculator entry and in the formula that you're using the z or the t distributions. Those are the two big probability distributions we've been using to construct these confidence intervals. Now the z distributions are pretty straightforward. We've been using these for a while. We use inverse norm, left tail area. Sorry, I just have to fit this in here. So inverse norm, left tail area 0, 1, or comma 0, 1. Remember that if you have the newer edition of the calculator, you might actually be able to get away with a central area or a right tail area, but we always showed left tail area in the notes. Or you can use the bottom row of the t table. For the confidence interval for the difference in matched pairs means, it's actually pretty easy. It's the t alpha over 2 that we learned back in chapter 9 as well, but it's just that the degrees of freedom is equal to the number of matched pairs that you have in your data set minus 1. And there we have it. Now that leads us to the worst one, this one, the t alpha over 2. Now remember, the true degrees of freedom for this is just absolutely atrocious. So what our book does is have you use the smaller of n1 minus 1 and n2 minus 1, which is an approximation. It's not great, but it's what we'll deal with for right now. But again, that's one of the reasons why we don't have you bother writing out the formulas for 11.3 nor for 11.1, but for different reasons. 11.3 is because you actually can't really know, well, I mean you can, but it's just an atrocious formula for the degrees of freedom for what an independent sample is for means. And rather than write that, I think I'm going to write what we're really going to do, which is we're not really going to find this one, and it's because the degrees of freedom is so darn difficult.